Good evening, everybody. My name is Jesper Freins, and I had the honor this year to work as team manager at Forze Hydrogen Electric Racing. And those two things, Forze and the team, are what I would like to talk about tonight. Forze is a one-of-a-kind project. It all started 13 years ago with a vision to make the world a better place. Back then, if you asked about sustainable mobility, most people only thought about battery electric vehicles. But the people at Forze, they thought about hydrogen. And they wanted to show the power of hydrogen by building zero-emission race cars. Now, this meant they had to deviate from the known road. They had to think outside of the box. And the people at Forze have kept doing that. We always move forward. And this you can see in our cars. But a vision alone does not make you unique. The people do. A vision does not become reality without hard work. And you need people for that. Good people. So, what are the people like at Forze? Well, they're students with a technical background, and they have a lot of ambition, motivation, and above all, perseverance. It is amazing to work in an environment like this, such a team. Why? Well, because we are a student team, every year a complete new team starts. Students that halt their studies, so they don't get any financial support nor study credits. What they get is what they have managed to achieve during that year. And that sets you out to accomplish great things. So, where do we start? We decided to develop world's fastest hydrogen electric race car this year. Well, normally, imagine if you would want to learn something new. You would look up a tutorial, you might read a book about it. But do you think we found this? A book on how to develop the world's fastest hydrogen electric race car? No, of course not. Innovation means you have to work hard and be perseverant. No one can tell you what to do. Yes, our alumni and our partners can help us, they can advise us, but at the end of the day, you need to climb up the ladder of innovation yourself. So where did we start? By looking at the growth of Forze and the innovation in the hydrogen and automotive industry, we found our achievable but very ambitious goal. We set our goal to race in the GT class of the Supercar Challenge. Krijgt na afloop van de wedstrijdleiding nog een tijdstraf voor hem. So, development started. We used all the knowledge we could get our hands on, in-house and from partners. We started by looking at our latest race car, the Forze 8. But the numerous challenges of developing the much faster Forze 9 quickly made it a totally different car. All went well, and we were working extremely hard. But then, an unfortunate situation for everyone. The coronavirus swept around the world. We chose to start working from home at an early stage to protect ourselves as well as the people around us. Our motivation and ambition allowed us to be dynamic and adapt quickly to the new situation. But our goal to develop the world's fastest hydrogen electric race car has not changed. We took this time to improve the design even more. And that is what we will show you tonight. None of this would have been possible without the hard work and dedication of our 100 alumni. None of this would have been possible without the hundreds of part-timers who also worked at Forze. But nonetheless, nothing would have been possible without the continuous support and belief from our sponsors and partners. They who believe as much in a clean future as we do. With this new car, we hope to bring even more joy to our fans and others that follow us on our journey. A new addition to the family, I dare say a breakthrough in sustainability, and hopefully an inspiration to many around the world. Ladies and gentlemen, we are very proud to finally show you Forze 9.
That looks pretty cool, right? Once I explain you how it works, it will look even cooler. I'm Antonio Scoccimarro, Chief Engineer at Forze Hydrogen Electric Racing, and today I will guide you through some of the amazing systems in our car. So, let's get started. The Forze 9 is a complex machine with many systems interacting. And like the human body, before it is able to drive, it needs a brain. This brain needs to activate and control the systems in the car, as well as check and monitor that everything works within the operational limits. The function of the brain is taken up by our embedded system, which has a central processing unit and distributed sensing and actuating units that act like the nervous system. As our car is a prototype with many custom-made components and experimental samples from the automotive industry, we need to monitor many more system parameters in order to validate our ideas and the ideas of our partners. This is what makes Forze truly special, as it is a lab on wheels on which the technology of tomorrow can be tested. Safety is extremely important in a racing environment, but it's even more important when working with new technologies like hydrogen fuel cell. This is why we developed a new component in our embedded system called the supervisor node, which is able to take up all the safety critical features and still work during a total system failure or power loss. This component is able to monitor our tanks and refueling system, as well as check high voltage electronics and be able to perform critical shutdowns safely. Now that the brain of the car is safe and ready, we can turn on the power. As most of you already know, our car makes use of a fuel cell system to generate the necessary power it needs to drive. Like a pair of big lungs, it breathes in around 15 kilograms per minute. That's more than an adult human can breathe in a whole day. The air is supplied to the cathode of the fuel cell through a compressor, while an intercooler and a humidifier regulate the temperature and humidity of the stream. The highlight of our air supply system is that we make use of a turbine to recuperate energy from the exhaust and boost our system efficiency. On the other side, hydrogen is supplied to the fuel cell through our pressurized tanks at 700 bars and is controlled through our custom-made hydrogen control system and ejector before it enters in the fuel cell and participates to the reaction. But let's have a closer look of what happens inside of the fuel cell. At the anode, hydrogen molecules are split into atoms and stripped of their electrons, leaving a proton that needs to pass through the membrane, while the electron is forced through an electrical circuit. This electron movement is effective current that can be used to drive the car. At the cathode, the proton bonds with the oxygen contained in the air and recombines with the electron, forming a water molecule. This water is then exhausted from the system using the excess air. What makes our car truly special and unique is that it runs on two separate and independent fuel cell systems. Only a few experiments have been done in the past on dual-engine cars, and this is definitely a first for fuel cells. Running on a dual fuel cell system like this one comes with several advantages, starting from redundancy that can help in case of a partial system failure, and reducing engineering risk, as one system can be developed and tested before producing the second one. Different control strategies and testing setup can also be run simultaneously and independently on the car, allowing our engineers to develop and iterate upgrades much faster. At the end, the world of fuel cell racing has still many challenges, and our car is designed to explore and tackle these. The two systems combined can produce over 200 kilowatts of power. This is twice as much of what we could produce with our last car, the Forze 8. But now that we have this power, how does it get to the wheels to generate useful traction for racing? This is where our advanced powertrain comes into play. Like the heart and arteries of an athlete need to provide useful oxygen and energy to the muscles, our powertrain needs to provide power from the fuel cell and accumulator to the motors. But where our powertrain differs from the human body is that it's able to recharge an energy buffer either with excess fuel cell power or by recuperating energy during braking. When maximized for peak acceleration, the system is able to output a total of 600 kilowatts. This is almost 100 kilowatts more than the Porsche Taycan, but comes with 800 kilograms less of total car weight. This boost capability is not just an extra feature to be used sparingly. The system is actually designed to achieve these powers at each corner exit throughout an entire endurance race. Now that the power can be delivered and used, let's see what our motors can do with it. Like an athlete has a pair of muscles for each leg, the Forze 9 will be fitted with 4 electric motors, each driving a wheel independently. Normal race cars are traditionally only rear-wheel driven, and only the most advanced Le Mans hybrid prototypes come with front-wheel drive, but neither have torque vectoring capabilities. With our distributed drivetrain design, we can enable full 4-wheel drive torque vectoring, resulting in extreme handling and cornering capabilities. This can be achieved, for instance, in a corner by spinning the outside wheel faster and actively helping the car to make the turn. Each motor can have a maximum power of 150 kilowatts and is designed to run at high speeds. To match the high rotational speeds of the motor with the relatively low rotational speeds of the wheel, we need a custom-designed gearbox. This gearbox, which comes with a fixed gear ratio of 12:1, consists of a bevel and planetary stage. This is a Forze first, and as far as we know, it's also a world first in electric racing. Taking inspiration from our old cousins, internal combustion engine cars, we decided to make the housing of the gearbox structural, in order to support the suspension members and connect the whole drivetrain assembly with the main structure of the car, the subframe. This results in a lightweight and compact package, which is easy to maintain and operate, and will ultimately result in a faster and more reliable car. Can you hear the motor spinning? Let's get on track. When going for a run in the park, you would never use your Oxford shoes, but rather a pair with good grip and structure to support your feet. The same difference exists between consumer road cars and race cars, where the latter need to drive tight corners at high speeds while accelerating and braking repeatedly. This not only puts strain on the systems as they have to operate in very dynamic conditions, but it's also very difficult to achieve without a proper interaction of the car with the road. A good suspension system can make the difference on track. Completely custom designed by our engineers, the double wishbone suspension needs to reliably transfer the loads from the car to the road and give the driver a good handling feeling. This is tricky to achieve with a powerful four-wheel drive car, as you need to combine the driving and handling characteristics with the tight packaging around the motors. As the suspension is so critical, it has been an important design input already at the early stages of the design, and led us to design our own custom monocoque. This full carbon fiber reinforced structure has the primary purpose of protecting the driver in case of a crash, but also houses the accumulator, front motors, and suspension. It has been very interesting for us and our partner to see how such a standard component in race car needs to adapt and change to fulfill the needs of such a radical and advanced race car design. The Forze 9 might have the explosive power of a sprint athlete, but as an endurance car, it is designed to be able to participate in marathons as well. Being extremely efficient and operating reliably is a must, but it's not enough if you're not able to keep your systems cool. Especially for an electric racing car like ours, it's extremely difficult, as most components need to operate at much lower temperatures than our counterparts' internal combustion engine cars. And the most effective way to cool such a racing car is to make use of the incoming air while driving. And to maximize this cooling effect, an aerodynamic bodywork is needed. Apart from the traditional aerodynamic surfaces that are needed to deflect the air upwards to create downforce for more grip, the main aerodynamic features of the Forze 9 are meant to redirect air through the 6 main radiators. Inlets at the front and side of the car scoop in around 200 kilograms of air per minute, while over 450 liters of coolant per minute is flowing through the radiators, exchanging heat with the air and keeping the car at the right temperature. Even with higher cooling requirements than other prototype cars, the Forze 9 still has a quite high aerodynamic efficiency, with a lift over drag ratio of around 4, which allows the car to slip through the air effortlessly. The aerodynamic design of the car has been iterated over 300 times, making use of computational fluid dynamics software. And the design has changed and morphed throughout the design process of the car to integrate seamlessly with the other systems. This integration philosophy has been adopted by all our members, without whom Forze wouldn't been able to push the boundaries in engineering and design such a beautiful and powerful zero-emission racing car, the Forze 9.
Thank you very much for joining us tonight. It has been a pleasure to show you what all the hard work of the people at Forze has gone into. I'd like to thank our partners and sponsors again for their continuous support, and this is where we hand over the design of Forze 9, world's fastest hydrogen electric race car, to the next team. Let's build it.